All right, good morning. We're going to go ahead and get started with our second learning lab of the semester. And before we begin this learning lab, we will be covering the various states of matter along with the various changes that can happen to the states of matter as you transition between the three that we will discuss. I want to go over some quick announcements. Number one, make sure that uh, you are submitting your learning lab assignment. So for those of you that showed up last week, you get credit for showing up, but you get the full learning lab and participation credit for sending me that learning lab assignment. You can do it again through either email, through a message on the Strong Mind site. As long as you get that to me, you'll get the full credit. Second announcement I want to make a reminder to all scholars to make sure that you are taking your iReady exams. We're at the mid-year point to take the mid-year diagnostic for English and math. So there was an extension to the deadline. They were supposed to all be taken by last Friday, but you were given now an extra week. So you have now until this Friday, I believe, to take those tests. So each one takes about 45 minutes or so. So make sure you take some time and do that. In terms of pacing on the course website, if you look at the announcement, so every Monday I'm going to be posting weekly updates that reminds you of when our learning lab is, and it also reminds you of what assignments are due that particular week. So for this week, if you look at the assignments, and you can also see it in your grade book, I believe, let me double check, but I believe by the end of this week, by Friday, you should be finished with Unit 1 Science Journal. So if you completed every assignment up to the Science Journal for Unit 1, you're on pace. If you haven't, then you can work a little bit quicker to catch up. And if you're ahead of that, even better. That's it in terms of my announcements. So before we jump into our agenda with our objective here, I'll open it up if there are any general questions about the course. Feel free to type them in the chat box. I'll pause for a few seconds. And if there aren't any, then I'll jump right in. All right, don't seem to have any questions, so we're going to go ahead and just jump into our objective for today. Scholars will be able to explain the properties of various states of matter. So we talked briefly about some of this last week, and this week, lessons 3 and 4 really jump into talking about those states of matter, what they are, how you transition between the three of them, and it all builds on that kinetic molecular theory that we discussed last week. So as our agenda, we're going to go ahead and take the first 15 minutes or so for me to guide you through an introduction of those states of matter and the matter changes. That's lessons 2 and lessons 3. After that, we're going to have some group practice. So that lesson 4 deals with the gas law. So it looks closely into one specific state of matter, which is gas. And it breaks down some laws and equations that are associated with that state of matter. So we're going to do some group practice with that. And then we'll finish up the learning lab with some independent practice and your learning lab assignment. Okay. So let's jump right into our first one, the guided practice of state of matter and changes on this, and I'll do it right here on the whiteboard. 3 main states of matter that you want to be familiar with as you go on through this course. Now, just for the record, there are more than 3, but for the purposes of this course at this time, we're only going to be focusing on our solid, our liquid, and our gas. Okay. Now, there are distinct properties in terms of, if you look at the molecular theory, the kinetic molecular theory of each of these states of matter. For example, in a solid, your molecules are all packed together. Is there movement? Yes, there is movement. There are little vibrations between the molecules that keep the solid somewhat moldable. So there are certain solids, say like Play-Doh. Play-Doh is a solid, but you can mold it, you can maneuver it, and that has to do with the little vibrations that exist in the solid structure. Okay. Obviously, if you have a more rigid structure, a more rigid solid, those vibrations are lower, and so it's more difficult to mold a rigid solid. But in general, if you look at the molecules, the atoms in a solid, they're very compact, very tight together, very little motion. If we move now into a liquid, in a liquid, your molecules are still more or less close together. However, there is enough separation between them so that a liquid can actually take the shape of whatever container it is placed in. So liquids in and of themselves don't have a shape. But if you place them in a container, then they will take the shape of that container. Okay? And if you take this same liquid and you pour it into a different container, it'll adjust to the shape of that. There is enough space between the molecules in order to allow for that to happen. Difference between that and say a gas, if you take a gas now there's enough separation between all of the molecules so that they will occupy the entire container that they are in. These molecules are moving extremely quickly, so the gas doesn't have any shape that we can visibly see for most of the time. And why is all this important? Because when we talk about energy, or when we talk about molecules, you're always talking about energy and the energy that these molecules have. Okay. So, a couple characteristics that you do want to know about solids. Let me lower my font. So you do want to know that they have a compact structure. Only possess little vibrational motion. And then the third thing you want to know for each of these is that a solid possesses very low amounts of energy. Why is this important to know? Because when we get to our next slide here and we start discussing states of matter changes, how you transition between a solid, a liquid, and a gas, you're going to need to know whether those changes require energy or whether those changes release energy. Okay? So just for the purposes of a solid, there's little energy because there's little motion. Always associate energy with motion. The more motion that you have in a molecule or from a molecule, the more energy that is being produced because that's what's causing the molecule to move. So in the case of a solid, you have very low energy because the structure is very compact to begin with. We'll jump straight to the gas. The gas has the highest amount of energy. Has a high amount of energy because the molecules are constantly in high-speed motion. Okay? Molecules are constantly in high-speed motion. And gases fill up any container that they are placed in. It's another thing you want to be familiar with. So gas molecules, very high in energy, they're moving very quickly, and they will fill up whatever container they are placed in. Okay? This is why we fill the tires of our vehicles with gas, because the gas will expand to fit the entire tire, inflate the tire, which is what we need in order to drive our vehicle. Finally, some properties of a liquid. Liquids have more energy than solids, but less than gases. This allows the molecules, they're allowed to move and adjust So molecules are allowed to move on a limited basis, but they move enough to take the shape of any container that they are placed in. Okay. And then again, if you're talking about the energy of a liquid, it falls anywhere between the energy of a solid and the energy of a gas. Okay, I'm going to pause right here and wait to see if there are any questions. Those questions can be typed in the chat box. Okay, it looks like we are pretty clear on the solid, liquid, and gas. So then what we're going to do now is jump into the states of matter changes. So you have solid, liquid, and gas. How do you transition between the three? And you're going to be running into terms that you might be familiar with, but the way we're going to discuss them is going to have to do with, again, just like everything else, with energy. Okay, so we're going to go ahead and jump onto the next slide and talk about state changes. As we do this, we're going to discuss the transition between solids, liquid, or gas. Okay. Solid, liquid, gas. A lot of this is going to end up being vocabulary that you want to be familiar with. Some terms you will already know, others you will not. Okay. Now, as we do this, I'm going to use two colors and I'll show you why. If I use red, what red is going to represent is an exothermic process, or an exothermic change, meaning that energy is released. So in order for energy to be released, it means you're going from something that has high energy to something that has low energy, and the energy has to be absorbed or released from that in order for that to happen. Let me write this in parentheses here. So moving from high to low energy. If I use blue, and I'll type that under here, the other vocabulary term you want to be familiar with is endothermic. Endothermic change. That would mean that energy is being absorbed, okay? Which means that in order for energy to be absorbed, whatever it is that's absorbing it is obviously going to move up in energy. So it's going to go from low to high energy. And for that, I'm going to use a blue color. Or purple, whatever this color is. All right. So let's go just in order. If you are moving from a solid to a liquid. You're going from that very compact structure to now you're giving the molecules a little bit more energy in order to move. That is an endothermic change. Okay? A solid to a liquid is endothermic. And the name that we give to this is called melting. Okay? So you're taking a solid and you are turning that into a liquid. You are melting it. Okay? It's endothermic, meaning that energy is absorbed, which means that yes, you need to input energy in order for this to happen, which makes sense, right? If you have something in the freezer that you're trying to freeze, say like soup, and it's in a solid state, and you want to turn it into a liquid, you're going to pop it either in the microwave or in a pan or in a pot and on the stove, and you're going to use either the radiation from the microwave or the heat from your stovetop to input energy and turn the solid into a liquid. Okay? Now, if you are going from a liquid to a gas, this is also an endothermic change. It does require energy as well. The process of going from a liquid to a gas is what we call evaporation. Okay? So when you evaporate, again, if you were to continue pushing energy into that particular liquid that you already melted, it would eventually give so much energy to the molecules that they would spread apart and they would turn into a gas, right? So when you boil water, say for coffee or for tea, you're turning that liquid, you see the gas coming out of it, you're burning some of those molecules and those molecules are changing from a liquid state to a gas state. And again, where is that energy coming from? From whatever you're using as your heat source in order to evaporate. Another word for liquid to gas, and I'll put it right here next to it, is boiling. Evaporation or boiling are both referred to as a state change between a liquid and a gas. So those two you may have been familiar with already. This next one that I'm going to write down, you may not have been. There is a way to go directly from a solid to a gas. And this is also a very endothermic process. It requires a ton of energy to do this. This process is called sublimation. Sublimation is it's such a drastic change in temperature that you are turning the solid into a gas directly, skipping the liquid phase. Okay? An example of this is dry ice. If you have ever seen dry ice comes in like a cube, it's a solid. However, if you expose it to room temperature, you'll see it start to emit gas right away. And that has to do with the fact that the boiling or evaporation point of that carbon dioxide, which is your dry ice, is very low. Meaning that if you just expose it to normal room temperature, it's going to skip right through the liquid and go into the gas state. Okay. That's sublimation. Those are the three endothermic changes that you do want to be familiar with. Okay. Let's talk about the exothermic changes. You can go from a liquid to a solid. Because you're going from atoms that have more energy and they're able to move in a liquid to atoms that have less energy in a solid, you are going to release some energy into the atmosphere. So this is an exothermic process, and when you're going from a liquid to a solid, we call it freezing. So that same liquid that you may have, say going back to the soup, you may have taken the frozen soup and you may have heated it up and made it liquid. If you want to freeze it once again, you want to put it in the freezer, because what that'll do is lower the lower temperature will absorb some of the heat that is released from the soup. That energy, that heat, that transfer of energy is going to move energy away from the molecules, so they're going to slow down and compact more closely. Which is what a freezer does, absorbs energy. Same process allows you to change from a gas to a liquid. anytime you change from a gas to a liquid, this is an example of condensation. Condensation is a process that you see in the mornings if you go out and you see vehicles that have windshields that are covered by what seems to be water. That has to do with the fact that the gas in the air comes into contact with a very cold windshield. The windshield will absorb the energy from those gas molecules, and in doing so, the gas molecules turn into water or liquid, which is what covers your windshield in the mornings. That's condensation. Again, it releases energy. And then finally, just like you can go from solid to gas, you can go from gas to solid. And I believe there was a journal topic that talked about this, if I'm not mistaken, a journal or a discussion topic. And this process is called deposition. Deposition is starting off with a gas and then lowering the temperature so quickly that you skip through the liquid phase. Okay, this is a process that is used in many industries in order to make either very moldable plastics that can also be firm in terms of solid and support a lot of weight. So you do want to be familiar with the term deposition, and again the fact that it is a exothermic change. When you talk about state changes, if you notice, we talk about them in terms of energy. You do want to be familiar with two terms that you're going to be seeing throughout the course. One of them is temperature and one of them is heat. Temperature is a measure of the average energy that an object possesses. So it's very easy to confuse temperature to heat. Temperature is just a measure of the average energy that an object possesses. We view it in terms of either degrees Fahrenheit or degrees Celsius, but all it is again, an average measure. Heat, on the other hand, heat is referred to as an energy transfer. So anytime that you have heat happening, it has to do with an energy transfer. Either you're releasing energy in an exothermic change, or you're absorbing energy in an endothermic change. Okay? So if you think of the ice in your drinks, if you want a drink and you want your ice to make the drink colder, if you were to describe that process in terms of a chemist, the chemist wouldn't say that you're putting the ice in your drink to cool off your drink. The chemist would say, I'm putting ice in there so that the ice can be warmed by my drink. Because energy only transfers from high, and I'm going to write that right here, energy is only transferred from high temperature to lower temperature. So in that drink, it is really the liquid that is transferring heat to the ice, which is why the ice melts. And in the process, because the liquid is losing that heat, the temperature of the liquid drops, which is what makes us enjoy our cold beverages. So energy is only transferred from high temperatures to lower temperatures. That's a kind of a rule that you want to always abide by. Are there any questions here? Okay. So here's what we're going to do now. We've hit states of matter and matter changes guided practice here. What I want to do now is jump quickly into our gas laws. Okay? So we're going to discuss more information about our solids and our liquids in the following units moving forward in semester 2. This particular unit asks us to look closely at gases. And there are certain laws that affect the way gases behave. And we call those laws gas laws. Okay? So in terms of the gas laws, let me make that a bigger. That's fine. In terms of the gas laws, the way gas behaves, gases are affected by pressure, by temperature. Okay? Pressure and temperature affects gas laws, and it does so in a way that determines how the molecules are going to move. So here's what I'm going to do. There's two main laws that I want to discuss today. One of them is Charles' law. The other one is Boyle's law. Now here's what I'm going to ask you to do. It is now 8:25. Between now and 8:40, there are a few things that I want you to do. I'm going to send you, each of you, a private message assigning you one of these laws, either Charles' law or Boyle's law. I want you to search the equation. The best place to find it is just in your Strong Minds course in Unit 1, Lesson 4. I want you to give me the equation for the law, and I'll give you whiteboard privileges so that you can write on the whiteboard. I want you to describe the law in your own words. And I want you to draw a picture. That explains the law. Okay, so two main laws. So what I'm going to do, I'm going to again assign you the specific law, give you until 8:40 to fill out the information, and anybody that I assign it to, you can write directly on the whiteboard and fill it in. And at 8:40, we're going to discuss both of those laws and run a practice problem. Okay? So what I'm going to do right now, I'm going to go ahead and get out of the way and let you work. After I assign you through private message whatever law you have, feel free to write on the whiteboard at any time. I'll assign you those privileges as well. And then at 8:40, I will come back and check in on these laws. Okay? And again, I'll be here so you can type in the chat box any questions as you're moving forward. Alright, it is 8:35 right now, so we have about 5 minutes left in case anybody wants to add any extra details to Charles' law, and then we still have a couple of blanks in Boyle's law. 5 more minutes. Alright, it is 8:40, so we're going to go ahead and pause with what we've written down so far for both Charles' law and Boyle's law. So we'll go through each one, make a couple of adjustments if we need to. Charles' law, both of these laws again explain how gases behave when there's a change either to their temperature or to the volume of the container in which the gases are in. So if you look at Charles' law, the equation is correct. Okay, so V1 over T1 equals V2 over T2. What does this mean? This means that 1 is our initial condition. So the volume of our gas initially and the temperature of our gas initially is going to be equal to the final temperature, the number 2, or the final volume of our gas over the final temperature. What does this mean in terms of, if you were to describe it? As volume increases, temperature increases. Yes. So there's no question mark here. You got it correct. Another way to see it, or to say it, is that volume and temperature are proportional to each other. Meaning that as one increases, the other one increases as well. Okay. And so I see the drawing down here. It says that if you have a smaller volume here, a container that's smaller compared to this large one, your temperature will be lower compared to the large one. And that's correct. So keep that in mind. With volume and temperature, the lower your volume, the lower your temperature. The higher your volume, the higher your temperature. They are proportional to each other. And why is that? Thing is, as you increase the volume, you increase the room over which the atoms can move. Because the atoms have more room in which to move, they will do so. And the more movement that you have, the higher your temperature, because that's where the energy measure comes from, how quickly things are moving. Excellent. Let's jump over now to Boyle's law. Boyle's law is a little different. Boyle's law relates volume as well, but it doesn't relate it to temperature. It relates it to pressure. Okay? So, let's start here with the description. For gases at a fixed temperature, pressure and volume are inversely proportional. This is beautifully phrased. Inversely proportional, meaning that as one increases, the other decreases. That's right. So pressure and volume always have this relationship in which as one increases, the other one decreases. Think about it in terms of a balloon. If you have a balloon, you blow it up, you increase that volume. There's not a lot of pressure in the balloon because there's so much room for the gas to move. However, as it shrinks, the pressure obviously increases because there's smaller space for the gases in which they can move. Excellent. Let's look at our equation now. PV equals K. It looks like it's close to like one of the laws that we're going to discuss next. But if we do it in terms of the way that we did the other one, P1, V1, your initial pressure and your initial volume, are always going to be equal to P2 times V2. So by definition, this is Boyle's law's equation. P1 V1 equals P2 V2, meaning that if you know the initial pressure and the initial volume of your structure, or of your gas, you can set that equal to the final pressure, and that would also equal the final volume. Okay. And in terms of the drawing, I see where whoever drew this was going. You want to show obviously that you have two containers with different volumes. So this would be the lower volume, and this would be the higher volume. The problem is that, keep in mind, our equation says that as pressure increases, volume decreases, meaning that they're going to be inverse. So instead of this arrow going up, if the volume is greater, the arrow would go down. Your pressure would decrease. And here, if the volume was less, your pressure would increase. Okay? So there's always greater pressure in smaller containers. Any questions on these two laws? So what I want to do in the 6 minutes that we have remaining is do a practice problem with one of these laws so that you can kind of see what you're going to be looking at. And then underneath that, I'm going to write your Learning Lab assignment for today. So we're going to divide this up. On the top, we're going to say So here we see a balloon has an initial volume of 2 liters and an initial pressure of 5 atmospheres. Atmospheres is just the way that or the units that we use to measure pressure. If the balloon is deflated to a volume of 1 liter, what would be the new pressure? So we're going back and we're looking to see our two laws. We have Boyle's law and we have Charles' law. Here we're dealing with pressure and volume, meaning that we're going to be using Boyle's law. P1 V1 equals P2 V2. Before you do anything with any of these equations, you want to write down everything that you have. So you read the problem closely. A balloon has an initial volume of 2 liters. So we know that V1 is 2. And an initial pressure of 5 atmospheres. So we know that P1 is 5. If the balloon is deflated to a volume of 1 liter, so V2, after whatever happens, we deflated it, our next volume is 1, what would our final pressure be? So this is what we need to find, P2. Okay? So I would rearrange my equation. In order to get P2 on its own, I can divide by V2 on both sides. My V2s would cancel here. So P2 is equal to P1 times V1 over V2. I know my P1 is 5. I know my V1 is 2. And divide that by my V2, which is 1. And I know that's going to be my final pressure, my P2. 5 times 2 is 10 divided by 1. Our final pressure would be 10 atmospheres. Which makes sense, right? I decreased the volume, and so by definition, I increased my pressure. Any questions on this practice problem or on these two laws? Cool. Let me write down your learning lab assignment for this week as we wrap this up. Tell me what the ideal gas law is. So again, you can do this through email or message. I want you to send me your definition based on what you research, what the ideal gas law is, and what the combined gas law is. Okay? So I want you to look those up, look up the equations, tell me what it is that they are doing or will use those laws for. Send me an email, send me a message, and you'll get that credit for the learning lab assignment. As we wrap this up now, I'll stop the recording, but I will stay here in case there are any questions. At 8:50, I'll start clearing off the whiteboard and everything for my next learning lab. So again, if you have questions, feel free to stay, type them in the chat box. If not, thank you so much for coming in early in the morning, and I will see you next week. Yes, Eliane, I'll jump back to